In total quality management, achieving quality at the time of delivery is only the beginning. True excellence lies in how a product performs over time, in real-world conditions, through wear, stress, and aging. This is where reliability engineering becomes a vital part of the quality journey. In this chapter, we'll explore how organizations ensure that their products not only meet specifications today, but continue performing tomorrow, next year, and for the full life of the customer's expectations. Reliability engineering is the discipline of ensuring that a product, system, or process will perform its intended function without failure for a specified period of time, under stated conditions. It is both a design philosophy and a data-driven science. It connects engineering, statistics, and quality management to predict, measure, and improve long-term performance. In simple terms, quality ensures conformance, while reliability ensures endurance. Reliability is the bridge between short-term quality and long-term customer satisfaction. A reliable product builds trust, strengthens the brand, and reduces warranty and service costs. In contrast, unreliability leads to repeat failures, downtime, and loss of confidence. No matter how well designed or beautifully finished a product is, if it doesn't last, it's not truly quality. Within TQM, reliability supports continuous improvement by feeding real-world performance data back into design, process, and supplier management. Let's look at some key reliability concepts that quality professionals should understand. Mean time between failures, MTBF, the average time expected between one failure and the next, commonly used for repairable systems. Mean time to failure, MTTF, used for non-repairable items, it measures the average lifespan before the first failure. Failure rate, lambda, the frequency of failures over time, lower is better and often expressed as failures per million hours. Reliability function, R of T, the probability that a product will perform without failure for a specified time period. Bathtub curve, a visual model describing how failure rates change over time, high at the beginning, low and steady during useful life, and high again during wear out. Together, these tools give engineers a language for describing how long and how well things last. Reliability engineering is not a single test or event, it's a closed-loop process, a continuous cycle of planning, designing, verifying, analyzing, and improving. Just like the Plan, Do, Check, Act model in total quality management, it ensures that reliability is not left to chance. It's built deliberately into every stage of the product lifecycle. Let's walk through each step in detail. Step 1. Define reliability requirements. Every reliability journey begins with clear, measurable requirements. We can't improve what we can't define. This step involves translating the voice of the customer into technical reliability goals. For example, a lighting control unit must operate continuously for 5 years with no more than 1% field failures. An aircraft sensor must function through 10,000 flight cycles without degradation. A joystick controller must survive 1 million directional actuations before failure. Defining reliability targets early ensures that design, materials, and testing all align toward the same performance expectation. It's not just about how the product performs on day one. It's about how long it can perform without compromise. Step 2. Design for reliability. Once requirements are defined, the design team shifts into Design for Reliability, or DFR. This is where potential failure modes are predicted and prevented before a single prototype is built. Teams use analytical tools like the following. Failure Mode and Effects Analysis, FMEA, to anticipate where and how failures might occur. Fault Tree Analysis, FTA, to map cause and effect relationships. Reliability Block Diagrams, RBD, to visualize system dependencies. They consider stresses, mechanical, electrical, thermal, chemical, and then build in robustness through material selection, component derating, redundancy, and simplification. For instance, in an electronic control board, capacitors are derated to operate at 60% of their voltage limit. In a mechanical linkage, designers may use self-lubricating bushings to extend service life. These choices are invisible to the end user, but they are the essence of reliability thinking, designing to endure, not just to perform. Step 3. Verify through testing. After design, theory meets reality, through reliability testing. Here, engineers create conditions that simulate years of use in days or weeks. They accelerate time by increasing stress, temperature, vibration, voltage, load, or humidity. To reveal weaknesses early, common approaches include accelerated life testing, ALT, determines how long a product can survive under elevated conditions. Highly accelerated life testing, HALT, pushes the design to its physical limits to identify margins and weak components. Environmental stress screening, ESS, used during production to expose those early failures that occur before the useful life phase. Each test is carefully designed to balance realism with acceleration. The goal is to predict life expectancy and understand failure mechanisms, not to simply destroy the product. Step 4. Analyze and improve. Once testing is complete, the data tells the story. Statistical tools like Weibull analysis, log normal modeling, or exponential failure distributions are used to describe life behavior. From these, we can estimate reliability at time t, mean time to failure, and confidence intervals, all critical to warranty planning and risk management. But numbers alone aren't the goal, learning is. Engineers perform root cause analysis on failures to understand why they occurred. Was it a design flaw, a material defect, a process variation, or a misuse condition we didn't anticipate? Once identified, corrective actions are implemented, redesigning components, adjusting process parameters, or updating supplier specifications. The new design is then retested, closing the PDCA loop. Over time, this cycle drives products from good to exceptional. It's how automotive systems last 300,000 kilometers, how aircraft fly safely for decades, and how electronics run reliably in extreme conditions. Step 5. Feedback and continuous improvement. The final step is perhaps the most important, feeding reliability data back into the organization. Field performance, warranty claims, and customer feedback all provide real-world insight into how products age and fail. This information is analyzed, trended, and shared across engineering, quality, and supply chain teams. The lessons learned are then built into the next generation of products, closing the loop between experience and innovation. This continuous feedback ensures that reliability isn't a one-time initiative. It's a living system of learning, aligned with the TQM principle of continuous improvement. In short, the reliability engineering process transforms uncertainty into understanding, and understanding into improvement. It's not about predicting the future, it's about designing for it. By following this structured process, organizations build not just reliable products, but reliable reputations. The best way to achieve reliability is to design it from the start. Design for reliability, or DFR, is a proactive approach that ensures robustness under real-world stresses like thermal, mechanical, electrical, and environmental. Some key DFR practices include the following. D-rating, using components below their maximum rated capacity to increase lifespan. Redundancy, adding backup paths or systems so that one failure doesn't cause total loss. Simplification, reducing the number of parts or interfaces, which statistically reduces failure opportunities. Environmental margining, designing to tolerate humidity, temperature, vibration, and shock. Test early, fix cheap, or so the saying goes, because the cost of failure prevention at the design stage is far lower than a field repair or a recall. Reliability doesn't stop at design, it must be maintained through the supply chain and manufacturing process. Key practices include supplier reliability audits and process capability studies, tracking field failure data and performing root cause analysis, applying statistical process control (SPC) to identify early drift, ensuring consistent component quality and traceability, conducting highly accelerated stress screening on early production runs. A reliable design can still fail if the process that builds it isn't capable, which is why reliability and process quality go hand in hand. Reliability also depends on people. Production errors, improper maintenance, or skipped inspections can all shorten product life. Building a culture of reliability means training teams to handle equipment correctly, follow standard work, and provide feedback when they detect potential failure conditions. Organizations with high reliability cultures focus on prevention, prediction, and learning, not blame. They ask, what failed, instead of who failed. Reliability engineering aligns perfectly with the pillars of total quality management. It supports customer focus by ensuring long-term satisfaction. It drives continuous improvement through data feedback loops. It enhances process control by linking design and manufacturing stability. And it reinforces evidence-based decision-making, using statistical reliability data to guide priorities. In this sense, reliability is the ultimate expression of quality, performance that lasts. Reliability. Engineering reminds us that quality isn't a one-time event, it's a lifetime commitment. Every reliable product is a silent promise kept to the customer that what they bought will perform as expected for as long as it should. So whether you're designing electronics, building aircraft, or manufacturing industrial controls, think beyond the delivery date. Think about durability, dependability, and trust, because in total quality management, reliability is quality that endures. This concludes Chapter 53, Reliability Engineering, ensuring long-term quality. If you found this video helpful, check out our other training videos in this series where we continue to delve deeper into the 6 pillars of total quality management, as well as tools, benefits, and how to implement TQM in your organization. Thank you for joining, and don't forget to subscribe for new videos from All Things Quality.